Alternating current fundamentals. Number 3. Measuring AC.
In the last video, you saw how the close link between electricity and magnetism forms the basis of operation for two common electrical devices.
You saw that when a conductor cuts a magnetic field in two different directions, voltages of two different polarities are induced. A simple generator was examined. You saw how it produces alternating current by using the principles of electromagnetic induction. The process describing how an electric motor develops its rotational power through electromagnetism was also presented.
In this video, an AC signal will be examined.
You'll see how alternating current can be measured, and sine wave terminology will be presented.
Now that you have some understanding of how AC is generated, let's see how it can be represented graphically. To understand alternating current, it's helpful to visualize voltage or current changes over a period of time. This can be done using waveforms.
Waveforms are graphic representations that show the magnitude and the direction of voltage or current at every instant of time. Let's see how a waveform is constructed. Let's use graph paper. Start by drawing two lines that meet at a right angle. The upright line or vertical axis is used to chart a range of voltage or current values. Positive values occur above the juncture, and negative values occur below. The polarity of a given signal will be determined using the vertical axis. The horizontal axis, on the other hand, can be used to keep track of the passage of time.
You'll see how this axis can also be used to indicate degrees of rotation, as in the case of an armature revolving in a generator. To help you understand how AC is produced and the waveform developed, a drawing that represents the voltage from a simple AC generator will be used.
The coil will be rotated clockwise between the magnetic north and south poles of the electromagnet. You've already seen in the previous video how the voltage output is zero when the coil is not cutting any magnetic lines of force. This is plotted as zero voltage at the 0 degree point on the horizontal axis. This axis will be referred to as the baseline. As the coil makes 1/4 of a revolution, the voltage increases from 0 to a maximum or peak value in one direction. The point at which the voltage reaches its peak on the vertical axis occurs at 90 degrees on the horizontal axis. As the coil continues to turn and completes 1/2 of a revolution, the voltage decreases until it reaches 0 again. At this instant, the coil is not cutting any magnetic lines of force and has completed 180 degrees of rotation. The coil continues to rotate, causing the voltage to reverse polarity.
Remember, this change of polarity occurs because the conductor is cutting the magnetic field in the opposite direction.
At 3/4 of a revolution, the maximum negative value is reached. This occurs at 270 degrees on the horizontal axis. From this point, the voltage gradually decreases to 0 as the coil completes its rotation. At this point, the coil has completed 360 degrees of rotation, or 1 full revolution. Notice the shape that has resulted. This waveform is sinusoidal and is known as a sine wave. Keep in mind that current would also form a sine wave because Ohm's law, E equals I times R, is equally as valid for AC as it is for DC. That is, assuming a constant resistance, any changes in current, I, will be directly proportional to changes in voltage, E. Therefore, the current waveform for AC takes on the same visual appearance as a voltage waveform, that of a sine wave.
Let's consider some important sine wave terminology. As a technician, you will need to know these terms.
First, let's look at a cycle. As an example, here are two cycles of an AC waveform. The area between any point on the sine wave and the next point at which the waveform begins to repeat itself makes up one cycle. The distance between the two positive peaks represents one cycle. Notice that this is exactly the distance between the two negative peaks, which also represents one cycle. The distance between any two positive or negative peaks of the wave is exactly the same as the distance from the first zero value to the third zero value, where again the waveform begins to repeat itself. Another way to think of a cycle is as a complete set of positive and negative values.
The word cycle is related to the word circle, so you can think of going in a circle as repeating yourself. This is exactly what the word cycle means in reference to the AC waveform. Let's look at a second important term associated with AC, frequency. The number of cycles generated in 1 second of time is called the frequency of the wave. The word frequency is related to the word frequently. Frequency indicates how many complete cycles of a sine wave occur in 1 second.
The frequency of a sine wave is measured in hertz, abbreviated with a capital H and a lowercase z. For example, a sine wave that completes 2 cycles in 1 second is said to have a frequency of 2 hertz. A sine wave that completes 5 cycles in 1 second has a frequency of 5 hertz. The symbol for frequency is a lowercase f, which represents cycles per second.
Understanding frequency is important because the electrical equipment that is powered by alternating current requires a specific frequency in order to function properly. There are many different frequencies. You can find many of them represented on the frequency spectrum. Let's examine it.
Notice 0 hertz or DC at the far left. Thereafter, moving to the right, all of the frequencies are AC. The low frequencies, those between 10 hertz and 1 kilohertz, are used for power transmission. In Europe, the frequency standard for power transmission is 50 hertz, while in the United States, it's 60 hertz. Note from the chart that audible frequencies, those that you can hear, are in the range of 20 hertz, a very low sound, to 20 kilohertz, a very high-pitched sound. Moving further along the spectrum, you come to higher frequencies used for television and radio. VHF, or very high frequencies, are those in the range of 30 megahertz to 300 megahertz. While UHF, or ultra-high frequencies, are those in the range of 300 megahertz to 3 gigahertz. Notice, too, that higher frequencies are used to transmit radio waves. Within these ranges are AM and FM radio. Notice from the frequency spectrum that at even higher frequencies, physiological action takes place. Infrared or heat waves, visible light, and ultraviolet light can be thought of as very high frequencies of electrical waves. As you can see, a further increase in the frequency results in radiation, such as X-rays, gamma rays, and cosmic rays. All of the technologies represented on the frequency spectrum, then, have a common thread. They are characterized by signals that are AC in nature.
Let's consider a third important term for AC waveforms, the period. The time it takes to produce one cycle, which you can find along the horizontal axis, is referred to as the period of the cycle. It's measured in seconds. The symbol for a period is a capital T, which stands for time. The higher the frequency, the shorter the period. If the frequency is 60 hertz, or 60 cycles per second, then 1 period, the time it takes to produce just 1 cycle, would be 1/60th of a second. The period of any given AC cycle can be determined by dividing 1 by the frequency. The formula reads T equals 1 over F. Become familiar with these 3 common AC terms.
Let's look at some different ways that an AC sine wave can be measured.
To do this, an oscilloscope will be used. The most apparent measurement of an AC waveform is its amplitude. This is represented by the vertical deflection of the waveform from the baseline. It indicates how far from the zero reference a positive or negative peak extends. The peak voltage is the maximum voltage on a positive or negative peak. It occurs at 90 degrees and at 270 degrees. The peak-to-peak voltage is the distance from the positive peak to the negative peak. It is twice the peak value. A third designation is the instantaneous voltage. This can be a measured value at any one particular moment of time along the AC waveform. It can be found anywhere between 0 and the positive or negative peak.
While these ways of expressing alternating current values have their use, another method is more helpful. Since electrical equipment can contain both AC and DC circuits, it's important to be able to express AC values in relationship to DC.
This is possible using the effective value. In a purely resistive DC circuit, the power dissipated by the circuit resistance is given off in the form of heat energy. For an AC circuit of the same resistance, the value of AC voltage or current that would produce the same amount of heat energy as the corresponding DC circuit is called the effective value. Therefore, an alternating current with an effective value of 1 ampere would generate the same amount of heat in a 10-ohm resistor as would a direct current of the same value, 1 ampere, flowing through an equivalent resistance. Similarly, an AC voltage of a certain magnitude, 10 volts effective, for example, would produce the same amount of heat as a DC voltage of 10 volts. The effective value is also called the root mean square, abbreviated RMS. The effective or RMS value of any sinusoidal voltage or current wave is always 0.707 of the peak value. In order to determine the RMS value, E sub RMS of an AC voltage whose peak value is known, you multiply 0.707 times E sub peak. Similarly, the equation for the RMS value of current is I sub RMS equals 0.707 times I sub peak.
Let's try an example.
For a peak voltage of 100 volts, an AC voltage would have a value of 70.7 volts RMS. This means that a resistor which is placed across a 100 volts peak AC source will produce the same heat as when it's placed across a 70.7 volt DC source. The RMS value is the one that is usually used to rate AC voltage and currents. The home line voltage of 120 volts is an RMS value, as is the 240 volt industrial power voltage.
This formula can be rearranged to find the peak value when the RMS value is known.
Divide the RMS value of 70.7 volts by 0.707. This yields 100 volts peak.
Distinguishing between RMS and peak values is important. Before going on, let's try an actual problem that will incorporate several of the values and terms to which you've been introduced.
Let's begin with the standard AC voltage coming into your home, 120 volts, which is an RMS value. Let's determine the peak value by applying the formula E sub P equals E sub RMS divided by 0.707. Dividing 120 volts by 0.707 yields 169.7 volts peak. This instantaneous peak value occurs twice each cycle, at the positive peak and at the negative peak of the cycle. What would the peak-to-peak voltage be? You can determine this by simply multiplying the peak value times 2, yielding 339.4 volts in this case.
Shortly, you'll have a chance to look at some of these values on an oscilloscope. But first, let's talk about safety. Safety is the most important thing to keep in mind when working with electrical and electronic equipment.
Here are 3 life-saving rules. Rule 1. Use one hand when testing and troubleshooting equipment. There will often be different levels of both AC and DC voltages within a single piece of equipment. If, in using 2 hands to troubleshoot, you accidentally come into contact with 2 different potentials of voltage, a current path is created directly across your chest cavity. The results can be deadly.
Rule 2. Make sure that your test equipment is in good working order. Power cords and test leads should be flexible and not frayed. Never use equipment when the ground has been clipped off the power cord.
Rule 3. Always use proper methods. Don't cut corners. When using certain equipment, such as an oscilloscope, all measurements must be taken with respect to the circuit ground reference. Damage can occur by connecting the oscilloscope across a component that is not referenced to ground.
Now, let's look at some of the values from the example on the oscilloscope. The AC voltage from the wall outlet can be brought into a transformer, which can be used to decrease or step down the incoming 120 volts to a more usable level.
Here, a 1,000 ohm resistor is being used as a load. Let's attach the probe leads across the load. Place the volts per division selector on 5 volts. The peak voltage in this case is equal to 3 full divisions and 4 minor divisions. Because each full division is set to measure 5 volts, the minor divisions will represent 1 volt each. To find the peak voltage, just add the values of the divisions together. 3 full divisions at 5 volts each is 15, plus 4 divisions of 1 volt each equals a peak voltage of 19 volts.
Keep in mind that there can be a positive peak voltage as well as a negative peak voltage.
In this example, the peak-to-peak voltage is equal to 6 full divisions and 8 minor divisions. With each full division representing a value of 5 volts, this makes a total of 38 volts peak-to-peak. Notice that this is twice the peak voltage.
Let's compare the oscilloscope readings with the readings on a digital multimeter or DMM.
Begin by connecting the DMM across the same load and selecting the AC voltage scale. The meter reads 13.43 volts, which is different from what we found on the oscilloscope.
Remember, the oscilloscope indicated the peak voltage. Let's convert this to a RMS voltage.
0.707 volts times 19 volts equals 13.43 volts, which is the RMS value indicated on the meter.
Let's check the peak-to-peak value by using the voltmeter readings.
First, convert the original RMS value to peak. 13.4 volts divided by 0.707 equals 18.95 volts peak. Now double the peak value to find peak-to-peak, which is 37.9 volts, or about 38 volts. Stop the tape and review this section again if you have any questions.
Now, let's see how Ohm's law works with AC circuits.
As mentioned earlier, Ohm's law is as useful in determining AC values as it is in the calculation of DC quantities. This is because in a purely resistive circuit, voltage and current are always directly proportional. Conversely, resistance and current are inversely proportional. The only conceptual difference between the AC and DC applications of Ohm's law is that while the voltage and current values in a DC circuit can be expected to remain constant, in an AC circuit these values are constantly changing. But for an instantaneous moment in a given cycle, the value of the current flowing at that instant is directly proportional to the magnitude of the voltage at that same instant.
Since all direct current rules and laws apply to alternating current resistive circuits, the AC power may be calculated from the measured voltage and current.
If the instantaneous values of voltage and current are multiplied and plotted, an AC power waveform is constructed. Keep in mind that whenever 2 positive values are multiplied together, the result is positive, And whenever two negative values are multiplied, the result is also positive. During the first half cycle of voltage and current, the power curve is in the positive direction. During the second half cycle, the power waveform continues in the positive direction. In purely resistive AC circuits, that is, circuits without any inductance or capacitance, the voltage and current waveforms will intersect the zero axis at the same time and will reach their positive and negative peaks at the same time. When this happens, the voltage and current are said to be in phase. For these types of circuits, the entire power waveform will be above the zero axis.
AC power can be measured directly in a circuit with a watt meter.
A watt meter has a scale calibrated in watts. On this meter, it's the bottom scale. Notice that there are 3 voltage terminals and 3 current terminals. 1 voltage terminal and 1 current terminal are marked with a plus-minus sign. They are known as the common terminals and must always be connected to the same point in the circuit. This is usually done by connecting them together at the meter terminals. Here is the symbol for a watt meter. And here is a schematic that shows the proper connection of the watt meter to measure the power consumed by a lamp. Let's hook it up. To connect the watt meter, the 2 common connections of the adapter cord are first connected to the meter. The current lead of the adapter cord is then connected to the 3 ampere jack on the watt meter. The voltmeter lead is then connected to the 150 volt jack on the watt meter. Complete the circuit by plugging the lamp into the adapter jack and the jack into an outlet. Insert a 100 watt lamp and energize the circuit. If your wiring is correct, the lamp should light. To measure the power consumed by the 100 watt lamp, depress the button marked watts and read the value on the 0 to 300 watt scale. The power measured is 95 watts.
Let's stop and review what you've been shown in this video.
In this video, you have been shown how AC can be represented graphically through the use of a sine wave.
You've been introduced to some important terminology such as cycle, frequency, and period.
The effective or RMS value was presented as a way of expressing AC values in relationship to DC.
Take the time to view this video again if you have any questions. A great deal of material has been presented. In the next video, 3 important devices will be examined that are used in AC circuits: capacitors, inductors, and transformers.